Hello everyone, myself Dr. Santime Kundu. I welcome you all to this lecture of soft computing technique. This is the fourth lecture of module 5. So in module 5 we have covered selection methods. We have discussed crossover technique for binary and real coded genetic algorithm. Today in this class we'll try to understand the crossover technique of order permutation coded genetic algorithm. So, in ordering technique for genetic algorithm, individuals are represented as permutations of a set of items, where the relative order of genes is crucial. These encoding types are common in combinatorial optimization problems, such as traveling salesman problems, job scheduling, or vehicle routing problem. Crossover techniques for ordered encoding must preserve the relative order and avoid repeating elements in the offspring. So there are many types of crossover technique for ordering encoding. First one is that precedence preserving order crossover or PPX. So in this crossover technique, there is a random vector of length n. There is a random vector of length n is randomly filled with the numbers 2 or 1s, which correspond the first correspond for parent 1 and 2 corresponds to parent 2. These numbers indicate the order by which the elements are taken from parent 1 and parent 2 respectively. The leftmost genes from the parents are taken according to the order given in the random vector, that is the 2 1 2 these vectors. When a gene is taken from a parent, it is drawn into the children chromosome and the same gene in the other parent is deleted. This step is repeated until both parent chromosomes become empty. So try to understand here that the parent O1, you can write it like 2, 4, 3, 6, 5, 8, 7, 1, 9. Parent 2 is that 6, 3, 5, 2, 1, 7, 4, 9, 8. And the random vector is writing it like RNV. So random vector written as RV is 2, the same length. So 2, 1, 1, 2, 2, 1, 2, 2, 1. Now offspring, so I'm writing it O1. So first one is 2 in the random vector. So the 6 will copy from there. So that is 6. So this 6 will be deleted. Now second is 1. So need to take it 2. So this 2 is deleted. Second is 1. So need to take 4. So this 4 is deleted. Second is 2. So 3 will come. So need to 3. This is 2. So 5 will come. So need to delete 5. Then first one is 1. So that will come from the next parent. So that is written as 8. So need to write it 8. So 8 is deleted here. So second is 2. 2 means you need to take it from. So 2 that is O1. So take it O1. Then 2 7. Then you need to take 9. So this is the offspring. In this way you will create the other one. So now next one is that position based order crossover. So choose n crossover points k1, k2 up to kn that should be the this such that n is very less than l, that is the length of the chromosome. The gene values of k1, k2 and kn are directly copied into the offspring c1, keeping their position information intact. The remaining gene values in C1 will be obtained from P2 in the same order as they appear, and they are already not copied from P1. we can reverse the role of P1 and P2 to get another offspring, that is C1 and C2. So here, if we write on P1 is like that, 1, 2, 3, 4, 5, 6, 7, 8. P2 is that 5, 6, 7, 8, 1, 2, 3, 4. So that is late offspring 1. So we are keeping at intact this position, genes are keeping at intact 3, then 5, then 7. So they will copy exactly that. So that is 3, then it is 5, then it is 7, then it is 8, then it is left. So 7, then dash. So remaining copy from the next parent. So here we need to take the parents from here in the order. So here we will get the already 3 is there. So we need to copy it here 6, 8. Then you can copy it here in the same order. So just it is like 1, 2 and 4. Already we have copied, so that not here. So in this way we'll get the offspring. So try to understand another example. So here P1 is written as P1 and P2. So P1 is written as A, C, D, E, B, F, G, H, J, I. And P2 is E, D, C, J, I, H, B, A, F, G. So now we K1, K2 and K3 given here, D be in that position. So that is third, fifth and eighth positions. So here offspring 1 for offspring 2. So here we can directly copy in that position, first, second, then that is D and C. So then 2 position left, then 1 position left, then you need to write B and I, then 2 position left, then you need to write H and A, then you need to write 2 position left. Okay, so first see the first is that E. So here you need to write P2, that is E, then C, D is already there, then J, then there is I, then there is H, B is already there. So it is I, H is already there, so we need to write here B is already there, so we need to write here A. Now you need to write here F and G. Similarly here A already there, so need to write here C there, so need to write here D. Here you need to write E, then you need to write here B, you need to write here F, you need to write here G, you need to write here H, you need to write here J. So in this way you will get the uh, offspring in this type of producing chromosome. So here the age recombination is another technique, age recombination order crossover. This crossover technique is used to solve TST problem when the cities are not completely connected to each other. In this technique, an age table which contains the adjacency informations but not in the order. In other words, age table provides connectivity information. So example is that consider a TST problem with 9 cities, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. Assume the two chromosome P1, P2 as parents. So P1 is 1 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 7, 7 to 5, 5 to 3, and again 3 to 1. So that is 1 to 2, 2, 4, 4 to 6, 6 to 8, 8 to 7, 7 to 5, 5 to 3, and 3 to 1. Another is that 4 to 3. So 4 to 3, 3 to 5, 5 to 7, 7 to 8, 8 to 6, 6 to 2, again 2 to 1 and 1 to 4. So there are two chromosomes. So now we need to write the CT. So from this connectivity, 1 is connected with 2, 4, 3. 2 is connected with 1, 4, 7, 6. 3 is connected with 1, 4, 5. 4 is connected with 1, 2, 3, 6. 5 is connected with 3, 7, 8. 6 is connected with 2, 4, 8. 7 is connected with 7 to 8. 8 is connected with 6, 5, 7 or 5, 6, 7. So step here is that let the child chromosome be C1. First is C1 or offspring 1 you can write. So let it C1. Start the child tour with the starting city of P1. So that write it P1 starting city of P1. So P1 starting city is 1. So here is connected with 1. So that is 1. So append the city X to C1. So first you write 1, then delete all the occurrence of the x from the connectivity list cities. So we need to delete all the one because already we reached in the one. From the city 1, choose the next city y, which is the least minimum for anyone. There is no choice connectivity links, and repeat these steps until the tour is not complete. So in this way we'll get it age recombination table. Next is the important technique, so which is known as partial mapped crossover or PMX. For some problems, it offers better performance than most other crossover technique. Basically, parent 1 donates a strip of genetic material and the corresponding strip from the other parent is sprinkled about in the child. Once that is done, the remaining alleles are copied direct from the parent 2. So informal procedure from parent 1 and parent 2. Choose a random segment and copy it from P1 to child. So suppose we are considering two chromosomes, that is P1 and P2. So we'll try to find their offspring 1. So chromosome is that 4, 1, 6, 3, 7, 2, 5. P2 is that 7, 1, 5, 4, 3, 6, 2. So suppose starting from the first choose a random segment and copy it from P1 to child. So this is a random segment copied from P1 to the child. So that is 6, 3, 7. We have copied. So that is the vacant place there. Okay. Starting from the first crossover point, look for element in the segment of P2 5, 4, 6, 3 that have not copied. So in this section we have not copied 5 and 4. 5 and 4 is not copied. Okay. For each of these I look in the offspring to see what element J has been copied in its place from P1. So in its place, that is the 5, in its place 6 is copied. Okay, so in the place of 5 the 6 is copied. So we can write this 5 is I and the 6th element J is 6. Place I into the position, that means 5 into the position occupied by J in P2. So J is 6, so here we need to put 5. Okay, so once again place I, that is 5 in the position occupied by J in P2. So that is J is 6, position J is 6, so we need to copy here. Okay, so now if the place of J is occupied, already been filled in the offspring by K, put I in the position occupied by K in P2. So 4, so in the place of 4, 3, so 3 is already occupied. So here I is 4, J is 3. So in the place of J, what position is that? 7. So in the place of 7, you need to put here in the place of 4 should be put in the place of 7. So that is the basically here we will get 4 and remaining are same. So here it will be and here it will be the 2. So that is offspring 1. Now similarly if you find interchange the P1 P2 we will get the O2. So once again try to understand that the partial mapped crossover or PMS. So procedure is that this is P1 and P2. Choose a random segment and copy it from P1 to the child. So random segment 637, copy it to the child. So we copied 637. Starting from the first crossover point, look for the elements in the segment of P2. So that is 5. So we can write it I. That is not copied 5 and 4. So that these two are I. For each of the I, look in the offspring to see what element J has copied in its place from P1. So in its place, 5 is copied. In the place of 5, 6 is copied. So we need to put the 5 in place of 6. So that is 5. So for each element I, look in the offspring to see what element J has been copied in its place from P1. So in the place of 5, 6 is copied. So place I, that is 5, in the position occupied by J, so need to put here 5. Similarly for I, J, K also. So here K is basically the 7. K is 7. So in the place of 7, put I, 4. So this is the partial mapped crossover. So try to understand it with the help of another example. So here the P1, P2 is that P1 is here P1 and P2. So we need to find offspring 1. If interchange will get offspring 2. So offspring P1 is 1, 2, 3, 4, 5, 6, 7, 8, 9. P2 is that 9, 3, 7, 8, 2, 6, 5, 1, 4. So there are total place is 9. So we can write it 9 place. So first one is that 4, 5, 6, 7. So let this strip is 4, 5, 6, 7. 4, 5, 6, 7. So there are 3 place and there are 2 place. Okay. Now step 1. So first crossover point is 8. So I can be written as 8. So in the place of 8, so in the place of 8, that is 4 is copied. So the 8 should be placed here. So J is 4. So 8 should be placed here. Okay. Next is not copied. 5 and 6 is copied. So next is that 2. So I is 2. So in the place of 2, in the place of 2, there is 5. 5 already copied. So there should be 2 should be kept in the place of 7. So there should be the 2. And remaining you can write as it is. So 9, 3, 1. So I hope you have understood how to find that. Similarly, try to find this thing also. So this is the known as the partial map crossover. So another crossover technique is that cycle crossover. So cycle crossover is designed to identify cycles between two parent solutions. Where a cycle is a set of positions that have same value across both parents. This cycle are then used to generate offspring by swapping the values between parents. So you can write a cycle crossover. So P1 and P2. So for P1 we are considering these things 1, 2, 3, 4, 5, 6, 7, 8, and P2 is that 8, 5, 2, 1, 3, 6, 4, 7. So offspring 1 and offspring 2. So here cycles is that from 1 to 8, from 8 to 7, from 7 to 4, and 4 to 1. So this is a cycle. So just scope it. So 1, 8, same position, 4, 1, then copy it from these things, then 7, 4, and 8, 7. So you copied it. Now interchange it. So 5, 2 should be here, 5, 2. So here is 3, 6. So then there is 2, 3 here. Then here is 5, 6. So this is the cycle crossover. Hope you have understood this crossover technique for order. Right? So different crossover technique offer different advantage depending on the problem type and representation of the solutions, binary, real valued and permutations. Selecting the right crossover method is crucial to achieve good performance in genetic algorithm as it influences exploration, convergence speed and the quality of the final solutions. Now, in genetic algorithms, there are two more most important terms, which is that crossover probability and mutation probability. So, in genetic algorithm, crossover probability and mutation probability are two key parameters that control the search process. These probabilities determine how often genetic operation, these are crossover and mutation, occur during each generation and significantly influence the algorithm's performance in terms of exploration and exploitation of the search space. So crossover probability, that is P small c. Definition: crossover probability refers to the likelihood that two parents individual will undergo crossover to produce offspring in the next generation. The role in genetic algorithm: crossover mimics the process of sexual reproduction in nature, where genes from two parents combine to form an offspring. Crossover allows the algorithm to explore new areas of the search space by combining the genetic material of two solutions. So typical range for the crossover probability is set between 0.06 and 1.0. So a value of 0.9, that is 90%, is common in many practical applications, meaning that 90% of the time selected parents pairs will undergo crossover. Implications: high crossover probability close to 1.0, more exploration, more offspring generated through recombination, which can lead to faster convergence but also risks premature convergence if not balanced with mutations. Low cross probability close to zero, less exploration and more reliance on mutation. This can slow down convergence but increase diversity in the population, which may help avoid local optima. Example: if you have 100 pairs of parents and a crossover probability is 0.9, about 90% pairs will undergo crossover, while 10 pairs will simply pass on the genetic material to the next generation without a crossover. Another one is mutation probability. Mutation probability refers to the likelihood that a randomly selected individual will undergo mutation. Mutation introduces small random changes to an individual's genetic makeup, providing a new genetic material that helps to maintain diversity in the population and avoid premature convergence. Mutation mimics the biological mutation process where random changes can lead to new traits of an organism. It helps algorithm explore new region of the search space that may not have been reached by crossover alone. The typical range for mutation probability is lower uh, than the crossover probability. It lies between 0.001 and 0.005, that is 0.1% to 5%. In most cases, crossover is around 1%. So high mutation probability, more random changes which may disrupt existing solutions. While it increases expression, it can also lead to an unstable search if mutation occurs too often, potentially preventing convergence. Low mutation probability, the search becomes more exploitative, focusing on existing solution and may suffer from premature convergence. However, it ensures stability in the evolution process. If we have a population of 100 individuals and the mutation probability is 0.01, that is 1%, you would expect about one individual to undergo mutation in each generation. How to set crossover and mutation probabilities? The choice of crossover and mutation probabilities depends on the specific problem being solved as well as the balance between exploration and exploitation. Balancing exploration and exploitations. Crossover explores the search space by combining different individual and therefore a high crossover probability close to 1 is often desired. However, too much crossover can lead to premature convergence where the population becomes homogeneous. Mutation introduces random changes that allow the algorithm to escape local optima and explore new areas of the solution space. If mutation probability is too low, the algorithm may fail and to find diverse solution and get stuck in local optima. So adjusting during run, sometimes it is useful to adjust crossover and mutation probabilities dynamically during the run of the genetic algorithm. For example, start with a higher crossover probability and lower mutation probability to encourage exploration initially, gradually reduce the mutation probability or increase the crossover probability as the algorithm converges. So, example, setting crossover mutation probabilities. Crossover probability set to 0.9, meaning 90% of the parent pairs will undergo crossover. Mutation probability set to 0.01, meaning 1% of individual will undergo mutation in each generation. In this scenario, the algorithm will combine parent solutions 90% of the time and introduce small random changes 1% of the time to explore new solutions. These settings strike a balance between exploiting the best solutions through crossover and exploring the solution space through mutations. So crossover probability controls the frequency of crossover typically between 0.6 and 1.0. High value means more explosion. Low value means less explosion, more reliance on mutations. Mutation probability controls the frequency of mutation typically between 0.001 and 0.005. High value, more random changes increase diversity but may disrupt good solutions. Low value, more stability, reduced exploration. Finding the optimal values for these probabilities often requires experimentation or fine tuning as they depend on the problem domain, population size, and other algorithm parameters. So, in this class, we have studied the crossover technique for crossover techniques for order coded GA and crossover probability, crossover and mutation probability. So question is that suppose we have P1 and P2 as A, B, C, D, E, F, G, H, I. P2 is that E, D, F, I, B, A, G, H, C. Find offspring 1 and offspring 2 by using partial mapped crossover. Suppose let the gene uh, let find offspring 1 and offspring 2 by using PMS. So offspring 1 is that, offspring 2 is that. In offspring 1 this is donated, so that you will get in the C, D, E, F is donated. In offspring 2 this is donated. You can write that this is O2 as, okay, so this is donated. So you need to find these values here from the P2 and these values and these values from p1. So solve these questions. So these are the references of today's class. Thank you.